everything for you. Another world. Yeah. Everything, everything for you. I make you do me, do me, do me, do me. Make you your own passport and Peter. Mona Lisa. Make I nearly down, start to show me more. Make I see now. Me I no carry Japanese for my eyes. So make you show me something we could do me strong thing. No, make you do me things we could make it bad man. Shock to me baby, shock to me baby. You did do the things we could make a lava. Oh, be like Drift. Oh, girl, you do me things we could make you me shout baby. She no need the visa to carry me dry by you. Everything, everything, everything for you. Enemies for you. Only me, only me, only me cover you. Everything, everything, everything for you.
I keep her check. She was a bad bad, nevertheless. Calling it quits now, baby, I'm alright. Needless to say, I'm keeping her check. She was a bad bad, nevertheless. Calling it quits now, baby, I'm alright.
Oh, make it do me things, we gon' make it bad man. Shock to me deep, shock to me deep. You did do the things, we gon' make a lava. Oh, be like Drift. Oh, girl, you do me things, we gon' make it me shout baby. She no need the visa to carry me dry by you. Everything, everything, everything for you. Enemies for you. Only me, only me, only me cover you. Everything.
Hello and welcome in, everyone. I hope you're doing well today and sort of getting ready to start sort of our session today. So just starting off with our agenda, we're going to start with our rules of engagement, then the main session, which will be run by myself today. We'll then go and move over into Q&A and then close out with some updates and announcements. All right. Cool. I hope you're all doing well, and let us begin. So just in terms of rules of engagement, if you do have any questions, please post them onto Slido, or alternatively, if there are more technical, you're welcome to put them onto AnswerBase themselves. Chat will be open ad hoc to interact with myself and the tutors, so if you do have any questions, please bring them forward. And most importantly, listen, learn, and share. All right. Cool. I'm going to stop on this slide for a second. For those that want to use Slido to ask any questions, please take a note of this, take your cameras out, and alternatively, you can just populate and use the link that is in chat at the moment. All right, cool. So with that out the way, let's get started. So random prompt for today, thought we'll do something different instead of a typical what do you call it? Serious talk. It might become a serious talk, but between DC and Marvel, which universe do you prefer? You can justify it in the comments. Let's see what sort of fan base we have. All right. So in my opinion, I think like Marvel does better to cinematically show all their characters off, but from a abilities and power level, I think DC smokes Marvel. But yeah, unfortunately, Marvel just does every single movie better. And yeah. Anyway, while you guys are discussing, and if we do start any fights, yeah, pick your superhero or villain, and then let's see. Great. With that sort of easy question out the way, we're going to start with our main session itself, right? And if you do have your best villain, more than welcome to share it in chat. Right. Today we're going to look at sort of an introduction to unsupervised learning, covering the major concepts that you will see throughout this modules. The reason behind this is we want to put a foundation through, so when we get into the purpose of coding it or working with any of the notebooks that talk of any of these topics, you at least have some sort of understanding about it, and we're not starting at sort of ground zero. So we will cover some topics you haven't yet covered in the course, but it's deliberate so that when we do get to showing you the practical aspects of it or doing some alternative talks, that it does make sense. So, an introduction to unsupervised. Our outcomes for today, we're going to focus on understanding the concept of unsupervised learning. We're going to look at the major techniques used and then the pros and cons for each and every one of these techniques. Now, they are subjective to my usage of them. I did try and validate it with some facts of the internet, but keep in mind that these pros and cons all depend on the sort of machine you're working with and various other factors involved. So you guys have at least had a chance to start and interact with the sort of this topic as a whole. I guess my first question to you in chat is just, what do you know, or what do you think unsupervised learning is? Machine learning without labels, learning without training data. Did you guys Google that, or is that your sort of preferred response? Any other takers? Anyone want to elaborate on that? Letting the machine figure things out for itself. Yes. All right, cool. I think we've got sort of a concept coming through. Learn from predictors only. All right, cool. Training computers to think for their own based off what they have been exposed to. Cool. I think we've got some good context here. So, unsupervised learning from a very definition based, right? Is to infer natural structures present, which involves identifying patterns, groupings, or distributions in the input data without any prior knowledge or explicit instructions about what to look for. And the reason we can't have any prior knowledge or sort of instructions we can give it is because we itself don't know how things should theoretically group, right? We're hoping that because of the uncertainty of what we don't know, we're hoping that the model can find those patterns and trends for us to move forward with. And sort of the easiest thing is we just don't have labels. So an example below, while they both look very similar, in the first thing, you've got supervised learning. This is what we've covered in regression and classification, where we've got our raw data, and this is then in the space of a training data set, and we know the desired output for this training data set. And it's got the space of a supervisor. We can validate these assumptions. We fit it through an algorithm, it processes it, and it'll give us the outputs, right? In the sense of apple, pear, and lemon. The alternative now, the sort of unsupervised realm, is while the data set in itself looks the same, there is one missing column, which is the output, meaning we do not have a training set or validation set. We then can fit this, though, to a model or algorithm, which can then process and tell us what it sees in the data set. Is there any relationships between the columns? Is there relationships between different data inputs and entries? And the output of that, while it might look like an apple, lemon, and banana, the process of this is that it's not going to tell you it's an apple. It's just going to tell you this is group 1. It tells you this is group 2 and group 3. We have to then understand why it gave us these groupings, and then we need to potentially add a label to it in terms of that segmentation. So the first one, supervised, it will tell us the label and we can interpret those results. Where unsupervised, it's going to give us these things and we need to make that inferences going forward. All right. So supervised learning from a theoretical point of view requires our labeled data sets. It aims to learn a function that maps inputs to outputs. Outcomes are typically quantitative and can be directly evaluated using metrics such as your accuracy scores, precision scores, F1 scores, or whatever metric that is available to us in the time. And what we normally use this for is sort of customer segmentations, anomaly detection. We're looking at like market basket analysis or sort of image compression. That's what we do with sort of supervised learning. From an unsupervised learning perspective, we're focusing on working with unlabeled data. We're aiming to identify the patterns and structures or relationships that exist. The outcomes are often more qualitative. So one is quantitative and one is qualitative, and 10 points to anyone that can describe it in chat before I explain the difference. And then you've got sort of spam detection that is done through unsupervised learning, image classification, sentiment analysis, and sort of medical diagnosis, right? So I think I might have switched those two around. But this is then what we're looking at when we're talking about supervised and unsupervised learning, right? And hopefully these sort of distinct differences can tell you what you're needing to do depending on the models that you are evaluating. All right. So seems that no one sort of's gone through to say what's the difference between sort of quantitative versus qualitative, right? So to start off with, quantitative, right, is a numerical based approach. It's something that's countable, and we can often measure this, right? Hence, we have metrics we can validate. Where qualitative, which is what comes out of your unsupervised learning metrics, is just a better way of interpreting and describing the data, right? So one describes it, the other one can be validated and sort of measured. Unsupervised techniques. Now, there are two major divisions of unsupervised learning techniques. One is clustering based and the other one is dimensionality reduction. So these are the two most common practices for these, and they break down in sort of two sort of subcategories that we'll speak about. Each of these methods have various pros and cons that we will discuss today, and you need to, as the data scientist behind the modeling, decide what is best for you in terms of how you want to process and work with your data. So we've got k-means clustering, hierarchical clustering, and dbScan. And from dimensionality reduction, the two major sort of pieces out there is PCA, which is your principal component analysis. And then we've got your TISNE, right? Is pretty much how it's said, is your T distributive stochastic neighbor embedding, right? So depending on your flavor, your data set, we tend to go and choose the appropriate clustering algorithm or the appropriate dimensionality reduction to better work with our data sets. So starting off with k-means clustering, right? This is used to partition data sets into k distinct groups, right? And the whole point is to have no sort of non-overlapping subsets. So no cluster is allowed to intertwine with one another. They have to be distinct and grouped accordingly, where K is the measure we're looking to evaluate them off. In order to produce k-means clustering, there are steps that we need to produce. And these are the steps. We start with our initialization, and this is where we select K. This is any value that we think is best to represent our data set. And this becomes our centroid, right? This is a randomly point that you figure out in your data set. And the whole benefit of this is because it's random, we can always update it and find the best version of it. This is just a guess of where you think the center is. So if you put your data set onto a scatter plot, you as a data scientist can guess roughly where you think the middle points of each cluster is. So that's the whole point of then having the benefits of k-means, where we can randomly place our values. Then we have the assignment, and this is basically we go and assign every single data point to the nearest centroid that we have created using Euclidean distance, which is circle geometry. And this forms your K cluster. So if we go with 2, 3, 4, we'll either have 4 centroids or 2 centroids, depending on the value of K we make, and then we'll get our groupings that formulate from that. We then, based off the groupings that we've made, we update the centroid to get a more accurate measure of it based off now all the new information it has. And we continuously repeat the assignment and updating process to get the best point of basically where your centroid will not converge, or alternatively, the maximum number of iterations are reached. We can't run the simulation again, or we've gone through all the options of K, right? And the output of this then is an algorithm that will give you K clusters with a corresponding centroid. Now, this is all very technical, so we're going to look at a practical example of K-means. So you've got the data set that exists currently, right? You've got 2, 3, 3, 3, 6, 7, 8, 8, 3, 4, 5, 6, 8, 9, and 6, 5. Now, we start by figuring out where we think the centroids will be, right? We can guess these. So we're going to say that we'll probably have a grouping around 2 and 3, and we'll probably have one at 8 and 8. Now, remember, this is just our initial assumption. From that, we take each point in our data set and calculate how close that is using your distance formula to C1, right? And then you'll do the same thing to C2. And depending on whichever distance is closest, that is the cluster that you will group this data as. So this is the manual way of doing it. And you'd go through the entire data set to get basically the various clusters. Once we have that, we then take all the new updated points and we calculate the new C1 and C2, so where we think that could be, and we repeat the step again of looking how close the new centroids are to the original points, and we reassign and adjust. And you can keep on iterating through this process until basically C1 and C2 stop changing, right? Or whatever version of it you choose to use. Eventually, at some point, you'll get to a number and it just stops moving. It just remains the same. And that's your sort of convergence level. And at that point, you know you either got the optimal amount of clusters and you're ready to proceed. So this is how the scatter plot looks. We have sort of C1 and C2 that will then be created from k-means clustering. So if we look at where those centroids would have been, this is where the centroids are. Those are the stars. And basically, the goal is then to put a circle around it, right? These circles are often perfect circles. I couldn't draw a perfect circle on C2, but that distance of that circle will be perfectly the distance of all points, right? So you technically, if you go from any edge to edge, it should all be the same. Obviously, just a very bad drawing on my point. But the purpose of it is that at the centroid is your star, and then you have a perfect circle going around that star to include your various data points. And obviously, you need a perfectly scaled graph as well so that you get the best representation of that circle. Now, there's some pros to k-means, and firstly, it is useful for various applications of segmentation. Next, it is scalable, so really useful to do on large data sets. And if you have anything that's got a large amount of data points, the model will be able to handle it quite well. It is a very fast algorithm, so it's able to compute at exceptional speeds, and that then sort of complements a scalability approach. And then obviously it's relatively simple and easy to understand, right? Find the center point of where you think things exist, draw a circle around it based on the distance you define, and then put these circles across a page. So hopefully that explanation is simple enough for you to interpret and go forward. There are cons, right? If you choose a bad centroid, it will take you a lot longer to get to your convergence point. So if you don't have a decent enough example of the data set, or you make a bad centroid, you will take a lot longer to solve the issue. You do need to have some sort of knowledge of this domain. So knowing roughly how many clusters you want. So for example, when you saw the graph I had, it was relatively easy to see we might have 2 clusters or so forth. But in a complex data set, if you do not know the domain, you do not know the segmentations you should be experiencing, you then will lead to very long time to process and work with the data sets to find your best clusters. It's limited to linear separable data. So in this example, we can technically draw a line through this and we can split that data. However, sometimes the clustering of points is not linear. You can't draw a line through it. You sometimes need to draw a circle or a square or some obscured shape, right, to create the best region to select these data points. Like typically a rectangle would work better here than a circle, because imagine the circle, if it was perfect, would have a very vast range. So it doesn't group very well. And that's sort of that con that we're speaking of, is that you can only separate things linearly because it's not allowed to have overlapping circles, which means some circles will be very large and you can't then have good intersects or separation that exists. And then the last thing is it's prone to converge onto a local optima. So depending on how you define that centroid, you can choose this point of where it starts to converge. So you don't have the best way to customize how that circle looks. You are limited, and eventually at some point there are going to be sacrifices in your clustering algorithm where you will miss certain data points and need to create an entirely new cluster in order to accommodate for any fringe cases of your data set. Next up, we've got hierarchical clustering. This is a method of clustering analysis that seeks to build a hierarchy of clusters, right? I know it sounds quite weird, but we'll talk about it in a second. There are two types, right? The agglomerative, which I hope I didn't butcher that, and the divisive, right? So the first one looks to basically merge the two closest clusters until all points are in one cluster, or until a stopping criteria is met, right? So you basically look for the two closest groups and then try and fuse them until you make one big cluster. And then eventually you get these big groups. The alternative one then is we start with very small clusters. So instead of joining all of it together, we start with two very small groups, see if they can work together, and then join them concurrently. So the one works from like a top-down or sort of bottom-up approach, and the other one's top-down. The steps to do this: we need to first compute a distance matrix. We merge our clusters. We update the distance matrix again, and we repeat this until we have the smallest distance between all points. Now, there are criteria we can use to create this distance mapping journey. First one is single linkage, and this is the distance between the closest points of two clusters. This is the default principle that people will use during hierarchical clustering. Alternatively, they use a complete linkage, and this is the distance between the furthest points of two clusters and trying to optimize there. The next method is the average linkage, and this is to get the average distance between all pairs to be converging to a single point. And then you've got Ward's method, which minimizes the increase in total within cluster variance. So again, trying to reduce the distance between each data points. To understand and use hierarchical clustering, there is something known as a dendrogram, and this looks very similar to your decision trees that you've covered before. So it's a tree-like diagram that records the sequences or merging or splitting of the data sets. And this is visually useful to see where groups of data exist and finding clusters in a very efficient manner. And it splits it in a very informative way to read. So things you need to know. There are leaves. The leaves are basically the individual data points. You've got branches. The branches are basically the nodes that are created and basically the various clusters that are formed at different stages of this algorithm. We then have the height. Now, to simplify this concept, the higher the line is, the more different things are. The lower the height of each given line, the more similar it is to the thing next to it, right? And I'll show you an example in a second. And the last thing is cutting. And cutting is basically a horizontal line that we can draw to split up our clusters. So given this theory of leaves, branches, heights, and cutting, right? The leaves at this point is A, B, C, D, E, F. Our branches, as you can see, let's bring the pointer, are these things, right? That's a branch, similar to decision tree. The height, you'll notice there's our first major split, and then we've got all these splits. So at this point, there is a very distinct group between anything between A and H, and there's a distinct difference between I and N, right? So these are the two groups you have initially. So if you had to create two clusters, those are the biggest or the easiest difference to spot. Then you'll notice there are some sub levels that we have different. This means these two are very close to each other, right? They're very similar in nature, which means they often might just be mistaken and can be grouped together. So depending on how far the point is from here to there, we then decide the number of groupings we want to create. And obviously we don't want to come too close to the bottom because then they are quite similar. So we try to find the highest point that creates a good division for us, and we're then able to create our relevant clusters. Right. So bringing color into it, or to then add a point where we cut these graphs, this is what it would look like. We create 4 clusters from our various leaves. The height was determined to sort of be here, where we create 4 distinctive clusters. If we chose to have a higher height, we would then have 2 clusters, or if we came further down because we want things to be a bit more similar between the clusters, we can then bring that cutting point down, or the cluster distance down, and we can create more subdivisions of our data set. And then the last thing is sort of your vertical cutting. And as you can see, we cut at that point to get our first cluster. The second one is sort of F to H, then I to L, and M to N. So at this point, we just chose the most distinctive points that we have the highest difference between the various groups. Now, these do take a bit of time to interpret. The main thing is that you need to understand that these are all your data points, or row items. The branches are then your various parallels of the algorithm. The height, the higher it is, the more distinctly different the stuff is. The less the height between the points, the lower the sort of, or the more similar they are in nature. And then cutting is just at what point are we creating our different cluster points. Pros of hierarchical clustering, right? It handles different types of distances and linkages quite well. It's suitable for very small data sets. So when it's easy to split and create that segment, as you saw, we only had, I think, roughly about 15 data points or whatever that might have been. It works quite efficiently to split. But imagine now having 1,000 data points and trying to create your tree of that nature. It's going to create a branch for every single point. And you can imagine it's going to become quite messy at some point, but it can work. It's got decent detection for any overlapping of groups, and because of the way it splits things into each individual branch / node, you have the ability to split the data points at a very accurate level. And it should be simple and easy to understand compared to some of the other stuff that's coming your way. Our cons, though. So it is computationally expensive, right? It's O to N to the value of 3. So as you keep adding new amounts of nodes, you can imagine this number grows exponentially quickly. So it becomes increasingly more difficult to run this algorithm. Different methods will give you different results. So we mentioned 4 ways to do linkage. If you choose either one of them, you will come out with a different analysis to that of your peer. So that is one of the major disadvantages of it. It's a very greedy algorithm, meaning it hogs a lot of the resources within your computer, and sort of very prone to being a biased representation of the data set because of how much it narrows due to the methods you choose. And the last thing is, obviously, given the computational expense and that it's a greedy algorithm, it's not very suitable for large data sets, being its con. So as you scale in, the effect and time that it takes to produce this diagram is increasingly more difficult. Next up, we've got dbScan. Now, this stands for your density-based spatial clustering of applications with noise. This is effective for finding arbitrary shapes. So as mentioned, k-means was a circle-based approach. Hierarchical looks at like a node tree-based approach. But what happens if it doesn't look like a tree and can't be split in that manner, and it's a large data set, and making circles everywhere isn't intuitive? Then this is where dbScan comes to the savior. Steps for producing a dbScan. We start with an arbitrary point on our data set. If that point is not assigned to a cluster, we can either mark it as a cluster point or mark it as noise. Noise in this case means messy or unneeded data. And we check its epsilon neighborhood. So we see how close it is in proximity to other data points. We determine if this is a core point, right? And if the point has at least a minimum point, we can then move on, or it becomes the new center point. From there, we expand the cluster and we check every single point around it until such point that we reach the value of epsilon, right? We'll talk about it in a less mathematical sense in a second. And we repeat this process for all unvisited points of our data set. So we manually check each and every data point to every other data point to every other data point all the way through until we get the point of everything falling within epsilon, which is the criteria we're benchmarking our cluster, and anything falling outside of those realms are known as noise or outliers, right? So to visually explain how this works, this is our data set on a scatter plot. We pick a random point in that sort of space, and we start with defining a distance. So we draw a vector line to the next data point, and we can either choose to create a circle, square, or whatever shape you want, right? Typically, it uses a series of different circles, but very small circles. I've just drawn a very big one, but it'll first draw a circle between these 2 points, then draw a circle there, then draw a circle between these 2, these 3, and keeps on going. So over time, it will evaluate all these data points to be in that circle. But to get to that point, it drew all the sub-circles, and it keeps on testing that. And the circle gets increasingly bigger and starts moving across the page. Now, I'm not going to draw all the circles, but it will infinitely keep populating circles. At some point, it realizes, well, now we're exceeding epsilon. It then moves on to say, well, let me find the next data point, right? That then becomes a new centroid or center point. And then it does the same thing, puts a circle and starts scaling itself up until it identifies that this is a different matching item, right? Now, there's a very simple way to sort of explain the algorithm and how it works, but it's because of the small circles we can create very distinctive patterns that aren't always just circles. Because if we had to draw 2 circles, they would touch each other, right? So eventually the circle area gets removed and we just keep reevaluating on new points. Now, the 2 benefits of this, right, in terms of the DB scan, and we'll show you another visual example, is it works really well with noise. So it explicitly identifies noisy data points that do not meet any criteria of our core principles that we lay down. These points are labeled to you. So the model itself will tell you this is an outlier. And for those that are working on different data sets and you often struggle to find outliers, this can be a useful method when we don't know the predictive variable. So historically, we found outliers based off its representation of its similarity to just the column we're working in. This now can look at all the data points and handle that space a bit better. And what happens is it will remove it from the cluster so that you have a cleaner representation of segments. Then you've got ASC, which is your arbitrary shape clusters. And this is the ability to create random shapes to form your groupings. So it doesn't have to be circles. And because it's working with very small circles, you can create any pattern. So it can even create a star in the end, or it can create a smiley face, right? I know it sounds quite weird. And due to it using density as opposed to distance, we then also have the benefit of getting really good clustering algorithms that come out. So an example of DB scan in practice, those are our data points on the top. We've got an epsilon and a minimum point value. And what will happen is it will create 2 groupings eventually. Now, I did draw circles for easy representation here. And then it will also be able to pinpoint that outlier on the top right of the screen. So based off that, it will spit out these clusters. And this is the resultant diagram that will create itself, right? It'll show you these 2 groupings and then also label your outliers for you. So it saves a lot of time compared to your k-means clustering and hierarchy, and that will pinpoint the outliers within your data set, or alternative word is the noise in your data set. Pros of this, it can identify clusters in any shape or form. It's robust to any noise, which others aren't because it always tries to fit them in. There's no need to specify the number of clusters. Because of the way the algorithm works, it will define clusters for yourself, which means you need less knowledge of the domain. And it is quite scalable, meaning it's able to handle large data sets computationally and work quite effectively through the data set. The cons: choosing your parameters, right, which is your epsilon and min point value, does require knowledge of the domain. So while you don't need to define your segments, you do need to define the range of which you want to include things with, which does make it slightly more difficult. The other con is that your clusters have varied density. So some clusters might be quite rich with data, where others might be quite sparse. It's less effective with high dimensionality data. So obviously, if you've got low data dimensionality, meaning you've got less columns, it tends to produce and perform quite well. So you're looking at things with 2, 3, 4, or 5 columns, works really well. As you start to go into the realms of 10 plus columns, it does tend to struggle a bit. Next is it is computationally quite complex because it's creating these micro shapes in between. While you do get very unique graphical representations of it, you will struggle to see how it runs from an algorithm point of view. From a maths perspective, it is quite hard. And I saw someone wanting to learn linear algebra, so you'd need to learn quite a bit to understand how this sort of computation works. Now to your dimensionality reduction world. So first one is principal component analysis. This is the process of reducing the number of random variables under consideration by obtaining a set of principal values. So how does this work? First, we standardize the data. So similar to regression, where we have to take everything and standardize it to make the numbers all in the same plane, we do the same here. And this is to ensure the data set is centered around the mean, so that you can see each feature as a unit variance. Next, we compute a covariance matrix. Now, covariance matrix is basically, depending on the number of features we have, we multiply that and get the same thing on the other side. So you take n times n to build a relationship between every single variable in the data set. Next, we compute the eigenvectors and eigenvalues. And what this means is eigenvectors is the direction of each given data point to every other data point. And then we get the eigenvalues, which is the magnitude, and this is the distance between that. So one is the direction, the other is the distance. And together you have then both distance and direction, right? And often we can then calculate something quite useful in the sense of a velocity. Next up is you can select your top eigenvectors. So we then choose based off the clusters or sort of data set we have, what is the highest number of vectors we want to produce. And from that, we then transform the original data set back to its original state based off the eigenvectors. Now, how does that look mathematically? So imagine your data set is on the left, all right? We're then going to standardize the data set first, which is why you're seeing everything on a different spectrum, and it's only between -2 and 2 and -4 and 4 for x and sort of y and x respectively. The principal component, right, in terms of the eigenvectors, is that green line and red line. And then you then go and calculate your eigenvalues, right, which is then the distance between each point. So they'll draw a line from the center to point 1, center to point 2, and it keeps on doing this to the point where it then gets to this final representation of saying, well, based off the sort of high dimension data that we had before, which existed between sort of -3 all the way up to sort of 9, we can reduce the size of those features quite significantly to make it more handleable or more computationally sound. Pros of using PCA is, firstly, it helps reduce the number of features. So that's dimensionality reduction. It allows you to get feature extraction. So if you are removing dimensions, which is your columns, you're in essence extracting features, meaning you now have the features that are relevant to modeling and can tell you what's important about your data set. It reduces noise, so any data points that aren't valid are then taken out of the equation. And it produces some really good data visualizations, which we'll show in a second. The cons of this, though, is that you lose interpretability of the data set because we're scaling it and adjusting it and tweaking the values of our data set. It's not always very clear and easy to understand. We're also reducing the number of features, meaning we lose information. It's sensitive to scaling. So depending on how you scale your data set or how the range of each column exists, you can tend to have issues when you try to scale the certain model values. So if we have to think of our housing data set, and let's say we were trying to group houses by a certain factor, we've got housing prices that are in the millions and bedrooms in the values of 3 and max 6. So between those two values, when we scale them, we can obscure the model quite drastically. And the major con of PCA, which is what the other one combats, is it's not able to capture non-linear relationships effectively. So if your data set is not linear, you cannot then find any way to use PCA effectively. This is then what welcomes t-SNE, or your T-distributive stochastic neighbor embedding. Now, what we do in this space here is that we use a non-linear dimensionality reduction technique, which is well suited for visualizing high dimensional data. So PCA is really good for low dimensional data that is linear, where t-SNE is good for your high dimensionality data that's not always linear. The differences between the two. As we mentioned, PCA is linear. It's used for reducing dimensions. The results are easier to interpret since it creates new orthogonal axes, right? So we can see the sort of demarcations it's creating. It is computationally quite effective and can handle large data sets. Now, the opposite of that then is t-SNE is used for nonlinear and focuses on preserving local structures. So it doesn't try to change the data set. It doesn't need scaling. It's mainly used for visualization. So it's not always used to reduce the data sets. It's often just used to create really good visuals. This often, because of the way t-SNE plots and doesn't reduce the dimensions or change anything from a scalability point of view, it is very difficult to understand some of the things that it's producing out. And computationally, it's very intensive and it's a lot slower. Now, to show you the difference between the two after the pros and cons, that will maybe become a bit more clear. But the pros of this is, as we mentioned, it works with non-dimensionality or non-linear dimensionality. It preserves your local data set structure. It's good for visual interpretation, and it's robust to noise and outliers where PCA isn't. The cons of this is you lose your global structure. Now, global structure and local structure. So local structure is just your inherent data set as a whole. Global is that because of the way it's changing and reworking features, you often tend to see alternative patterns that you're not familiar with. The parameters are very sensitive, so tweaking anything in a t-SNE model can drastically change the way it creates your visuals. There is an interpretability challenge due to inherent variability of data in your data set that you have, and as you mentioned, it's computationally expensive to do it. Now, this is an example of PCA and t-SNE running side by side. So PCA will create segments for you, right? And you can see that on the screen. It allows for that overlapping effect of data points, but it is often quite difficult to read, right? The good thing is, though, that because everything's on the same scales and spectrums, we can kind of read and interpret our groups, right? We've got a grouping there, one group there, a mix of groups and stuff here. And the problem with PCA, as you can see, is that there's this very bad overlapping that's occurring. Where t-SNE will change these things. So you will create distinctive groupings that are easier to handle. However, the segmentation between points is then lost. So now everything gets grouped to then create this disparity between groups. And that's where it becomes a bit more harder to interpret afterwards. But visually, we can see the groups better, which is why it's good for visual analysis. But in terms of understanding why that happened, that's where it gets a bit more tricky. All right. Whereas on the PCA side, we can see why there's these groupings. We can see there's an overlap, and we can see the data range that this overlapping is occurring. So the question I have for you at this point, right, is can we merge, based off all the knowledge we've just covered, unsupervised learning with supervised learning? And this is where we're opening up the discussion space. Okay, everyone just saying yes. No one saying no to challenge the standard quota. One person says no. I'd love to know why you said no. And also all those that are saying yes. And the next step of this is for us to discuss why, or how do you see them working together? All right, so we're going to now look at it or talk through an example while the slide's on. So supervised needs a label, right? Unsupervised can create a label for us. So if we look at the previous slide, well, right? If we use the TISNI results that come out, we in essence can label things as whatever grouping we want, group 1, group 2, group 3, group 4, all the way through. And we can attach that to every single one of those line items, meaning we now have created what is known as a semi-supervised learning model, right? And all that means is that we've created artificial labels. We can validate these labels later on once we've seen history or seen the future unravel. And then going forward, we can adjust the supervised model better or the unsupervised one to create better clusters for ourselves. So that's sort of the intersect that can exist between the two. Alternative use cases of this is, imagine we have a data set that has 30 columns. Are all 30 columns always relevant, right? There are things that you guys have done in the past, or you've done feature importance and so forth to extract important variables. However, what if we look at a smarter way of reducing those features? So instead of running an entire model to train the data set and then test accuracy and get our results out, why don't we do something that runs through the data set to find groupings of our data, which is what unsupervised does. And once we've got these groupings of common columns, important columns, we then move forward into the modeling space. So it can save us time in terms of not needing to evaluate all 30 columns of our data set. We can start with 10. So it speeds up the model journey for ourselves. And we are then able to move more progressively in the right direction for modeling. So it's meant to save time, but unless you absolutely know how to use things hand in hand, know the pros and cons of using any of these principles in unsupervised, you will sometimes make more work for yourself, right? So use the simplest approach, one you're comfortable with, but as you evolve and become more mature in the sort of data space, quite often you're going to work on projects where there is no labeled data sets. And you're going to need to go through unsupervised methods to firstly reduce your data set size because there's always unnecessary columns. You're then going to need to create distinct segments to handle and work with the data sets. And often by creating these segments, we help in terms of understanding the different domains that we're working on. And then we can offer a different layer of analytics that wasn't present because we didn't have labeled data set. So that's how you use these interchangeably, right? But there is a risk to it all because by you creating poor clusters, you can often then create poor labels that then affect how we perceive a certain grouping that is then created by the model, right? And if we obviously train the model to think that this is the grouping structure, it will learn that and it learns off the bad behavior set up at the start. All right, cool. So, in short, to answer this question, yes, we can merge unsupervised and supervised learning techniques, right? It's a matter of what you feel most comfortable with. And often, sometimes the theory and stuff that we've learned in our supervised realm can come through to support our unsupervised learning models in terms of interpretability and so forth. But more often than not, you're using two different model tech stacks. You can't always use algorithms that are unsupervised for supervised learning models and vice versa, right? So there isn't something that's generic across the board, but there is a sweet spot where they can communicate with each other and share similar insights for you. Right. Now, a lot of theory, technically covered, hence sort of kept it quite short. The next webinars that we're going to evolve on is how to actually then implement these changes, right? So looking at k-means clustering, how it works, practically doing it and running through, I wouldn't say the maths behind it, but the actual code needed to generate and informatively understand and interpret k-means, right? And so forth. We'll build the way through, all the way through the various topics of the weeks that are coming your way, right? Cool. Now I'm going to sort of go into Q&A. And if you do have any questions, please pop them either, as we said, sort of on Slido, or alternatively, there is some on sort of the spectrum here that we have, right? So we've got a question, right? So the first one was the min point was 2 and epsilon was 1.5, yet the outlier was 1. Why is that? So I'm going to go back to that given visual very quickly. So I think we're referring to this one, right? So the outlier isn't 1, it's the data point 25 and 80. And typically, if we draw epsilon's distance between these data points, it realizes that it's way too far out of that spectrum to be considered part of any of these clusters, right? And we also chose 2 min points. We didn't choose 3 or 4, which means we got the sort of segmentation. So the outlier in this case is 25 and 80. From the human eye, it's very easy to perceive this, right? But as we get more complex data sets, the algorithm of DBScan will do it for you. So instead of you needing to computationally calculate the outlier for each group or line item, DBScan does it for you. So it's a smarter way of optimizing the sort of searching parameters for an outlier in your data set. Sort of that's hopefully answering that first question, right? So the outlier was not 1, but in fact, data point 25 and 80. Right. Cool. Right. Is there any news about our final exams? Format, at the hub, or remote? Timed or no retry? So your final exams are going to be untimed. Now, we do know that you guys had an issue with the time test for the classification exams that we had now. If you were affected, drop us a message. We will reset it for you, provided it is a warrant, right? That you actually were genuinely impacted by that time effect. We won't fight you, but don't just ask for a sort of retry just for the sake of it. Your final exams will have retries and will work off the supplementary attempt that you've had before. So there'll be a mix of MCQ and potentially coding challenges. So MCQs, you know the drill, 1 retry before the deadline, and sort of 5 after the deadline. And then coding challenges, unlimited retries before the deadline, and obviously 10 supplementary attempts. So that's sort of how it will work. There is no timers. We will indicate how long it should take you to attempt these exams, and they're all going to happen online, right? So you are able to go to a campus and write it if that is for your convenience and you feel more comfortable, but you are able to take these exams at home as well. Right. Cool. All right. Next one. Cool. First, it took the time. Are we going to be given a chance to retake? Yes. So if you were affected by the time theory exam, you can retake the test. Note that all your progress will be wiped off. Right? Cool. Next up. Can you provide insights on issues such as overfitting, computational complexity, and interpretability, right? So very seldomly are you going to see overfitting with the sort of algorithms, right? They are highly sophisticated, meaning they have the ability to reduce itself to overfitting issues. The only risk is that you made your sort of k-means cluster or your epsilon value too high in certain cases, and you've created bigger clusters than you should have. So in this example that we're looking at now, a result of a very poor underfitting example is that you choose an epsilon of like 5 which means you will include all of this as point one, and that'll be group one, and your group two will then be this point over here because your epsilon value is too big. So you are at risk of underfitting and not creating small enough partitions. At no point are any of these models tending to overfit at any time, right? It's not something very possible, just due to the maths. From computational expensivity, like follow the pros and cons. Obviously, I don't remember them all offhand, so you will have to cycle through the slides that I will share with you. But choose one that works for the size of your data sets. Start with the easiest of them all. So, for example, k-means, clustering, and PCA are the quickest for you to apply in most data sets. As you grow and you want to get better clusters, then you come to dbScan, which is more computationally expensive, and then you will then refer to the likes of t-SNE for better visualization and practices. So you start with the basics, but at the end, you will end off with dbScan and sort of t-SNE as your go-to for creating your clusters and dimensionality reduction. So hopefully that makes sense. And in terms of interpretability, it all depends on the data set. So that's something we'll try and produce through the examples and practicals on a Thursday, is to show you how to read and interpret different dendrograms, different clusters, and so forth, and how best to move forward and make smart decisions thereof. Right. Cool. Next up, how is unsupervised learning used in anomaly detection? What are some of the examples, right? So think of your banking history, right? You obviously have transactions that are recorded as line items. So it has a date, it will record your region, it records the area that you're in, it will record the time of day. Those are all happening, right? And then obviously they know your home address, right? So these are normal, it'll track these behaviors and then see, cool, Damien's made a purchase. I'm going to give you an example. I live in South Africa and I live in Gauteng. Pretty much any transaction that I do within Gauteng, provided it's during my normal transaction times, will go through without any detection because it's normal, it's part of the pattern, and they will all cluster together. As soon as I try to have a transaction outside of the country, let's say I haven't worn my bank, and I also haven't bought a ticket on the banking app, right? Meaning there is now this gap between Damien's normal trends, which are all flagged to be within South Africa and Gauteng, and now all of a sudden a US McDonald's is flagging an order. That will be an outside anomaly. It'll be flagged as a noise or an outlier by a clustering algorithm. And from there, we can flag that as a fraud model, right? A fraud incident. They can then do validation to see have I left the country and so forth before they reach out to suspect fraud. More often than not, banks will go with the safest route and block the transaction first and then look to authorize it later on once they've validated, because it's far easier to resend money than to get it back once it's gone. So that's an example of unsupervised for anomaly detection in banking, right? Alternative ways is if you've got water supply that might be happening, it's looking at your general trends will all group and confine to certain patterns. And as soon as something happens outside of that pattern's normal distributions, parameters, confidence intervals, then that then creates an anomaly event that these clustering algorithms can in essence find and detect on a continuous basis. Right. Any updates on FIS? Unfortunately, I don't think there's an update on FIS just yet. So once we do have it, I do know it's coming to Circle. We had a chat on Monday, which was yesterday, and we're hoping to get an update by Wednesday, which is tomorrow. As soon as there is an update, we will make an announcement. It will occur here on our webinars and also on sort of any other platform that we can share and communicate with you. Right. Cool. After completing course, what are you likely to hire us for? So if you're asking us, Sand, what we would hire you guys as, we have tutors, we have community ambassadors that people could fill in those roles for. Obviously, I can't promise anyone a job, but those are roles that exist that we can hire for. There are obviously data scientist roles, data engineers, which are more senior, and depending on your proficiency, your background, those opportunities can come alight. And if you are curious about any opportunities at Sand Technology, you can go to Sand Technologies Careers, and there is a useful link to all job offers that exist within our organization. Right. And if you're good enough or know someone in Sand, there's also a referral policy that can work. Cool. Right. Next is, do I think you guys can qualify for a junior data science position after this course? If you've got, and I'll be honest, in the job market, if you have a STEM degree, which is statistics, technology, engineering, or maths degree, and you've done this course, there is a good chance that you can go in as a junior data analyst, junior data scientist. However, without those, you are then leaning to more of a data analyst. And that is just because of the way in which these job contracts are spec'd by the hiring managers. So unfortunately, there is a bias of wanting certain degrees to come into the space. And if you've got people to vouch for you, I think very comfortably you can walk into a data science position, provided you are confident with all the foundations that we've taught you. So every single topic we've covered in this course, you do need to have a very broad understanding of it. However, if it's limited and you're not so confident on the machine learning aspect, you're not comfortable with sort of operational and data engineering, then you would want to put yourself as a data analyst on the market. All right. Cool. So it just depends on the companies, your reach and sort of targets. And I can advise on a more individual capacity if need be. Cool. Michael, if you don't mind just sharing your email address, we will send you an email for AnswerBase. Unfortunately, I just need your email address to send you an activation code. All right, cool. I'm going to switch over now to Slido to see if there are any questions on that format that I can then tackle. Right. What is the difference between variable selection and dimensionality reduction? So variable selection happens in terms of comparing how a variable correlates with the predictive output, right? So a input correlation to an output. Dimensionality reduction does not do that. It looks at relevance to a sort of data set. So it's comparing each sort of point and entry with every other point and entry in space, right? So that's the difference between the two. One is input to output, where the other one is purely just comparing all the various inputs to every other input and whether there's relevance to each other in that spatial awareness, right? Cool. All right. Cool. Thanks, Michael, for the email address. I will copy that and send you an email shortly. Cool. All right. Great. Next up, I have two questions. When will FIS resume? I can't answer that one, unfortunately. I know it's coming soon, but I cannot give you an exact thing. And then what is the purpose of the points given in answer base? So answer base points is just, it's tracking how many questions you've answered. Have you upvoted things? So it's just a metric that answer base provides for us. This allows us to see if you're active on that platform and supporting learners or supporting each other or engaging. It doesn't contribute to the overall course thing, but if we are looking to hire you, I'm probably going to look at answer base to see if you've answered any questions in the past. So no direct implications of not using answer base. It's more for your own benefit. It's a fun scoring metric, and it doesn't contribute to the course in any particular manner. All right. Cool. Next, someone's asked for sort of a webinar on linear algebra, right? I think we can potentially pose to do that. I do know that it's a very tough concept to cover just because of depending on what people studied historically, which does make it quite difficult to then help everyone understand the topic if there's no prior maths knowledge. So we can look to see how to integrate it. For now, we'll look at easier ways to implement dimensionality reduction through code based. And then once everyone's comfortable and there is time, maybe we can do a webinar looking at the mathematical background of these algorithms that we spoke about and techniques that we covered today. All right, cool. The other ones all seem to be answered quite well. So I'm actually going to pause there. If there is any other questions now's your time to pop them into the chat if there is anything else that you would like us to cover now. Alternatively, while you're thinking of your questions, we're going to launch the poll. So if you do have any things, basically, do you understand what unsupervised learning is about? Its basic principles, the major techniques that we use, and the pros and cons behind them. I am going to exit the screen for a second because I do know people are going to want the slide deck. So just give me a second. I want to share it with you now. Because obviously I did mention that we are having issues sharing the stuff quite easily. We are working on that repository, and once I have that, you'll have a far easier way to access all our historical content. But for now, there is a link in chat to access the slide deck. Cool. All right. So populate that poll, and then I'm going to then swiftly move over to our updates and announcements. So firstly, the deadline for the NLP classification was extended till today. So you have until midnight today, depending on where you are based. So 9:59 GMT to get that in, right? If you are affected and want to resubmit or attempt anything differently, please make sure that you go and ask the tutors on AnswerBase or your community ambassador, and we can support that relatively quickly. If for some reason you can't get to redoing the test today, please make sure you let us know in advance or work very actively to get those tests in so that we can make those accommodations for you. Next up, your first assignment for unsupervised learning, which is dimensionality reduction MCQ, is Monday the 27th, 9:59. For MCQs, it's a friendly reminder you have 1 attempt before the deadline and 3 supplementary attempts after the deadline. So make sure that you know you don't have unlimited retries. There is no time on this test, so make sure you get your submissions in before Monday. We will have a webinar watch party for today's session, which will happen tomorrow. And our next webinar is scheduled for Thursday. As mentioned, we want to go a little bit more technical, look at some coding practices for some of the components and try to get into the theory and explanation of understanding and reading the various algorithms that we're mentioning at this point in time. Last announcement from our side is to please participate in your study groups, discussions, connect, learn with your fellow peers. And there is one more that I sort of remembered right now. We do send some very important communication through email, so please ensure that you are regularly engaging with your emails as any important updates that we want to share with you are taking place there. So please open those emails, make sure you're reading them and getting the contents that we want to share for that given week. Awesome. Right. A friendly reminder about our support channels, right? AnswerBase is going to basically be for all your technical support. Then you've got Layer, your Zendesk, which is your chatbot for any interactions or questions you might have. And then your normal community space, which is the fellowship for your day-to-day interactions with peers and program teams. Right, I do see a question that happened in chat, and hopefully Buhari will tackle that. And then we just need your name on Athena to then provide that reset for you. Cool. Right, that is all for today, right? So welcome to sort of unsupervised. Well done in getting to the final machine learning sprint in our data science course, right? From here, sort of, you hopefully will cover a lot more theory than normal. Slides are currently in chat for those that want it. As I said, the repository is coming very soon, and we'll be able to then share the one-stop shop for all webinar content, slides, notebooks, etc. Cool. Until Thursday, I hope you all have a fantastic day. Please do reach out to us if you do have any questions regarding your resetting of your tests and so forth. And we will make the sort of necessary changes and updates to Athena to allow you the ability to reattempt that test. Note that all your answers will be wiped. So if you do ask for a reset, make sure you submit, or else you will get a 0. We won't record that previous mark or submission that you made. All right. And with that, have a fantastic day. Until next time, cheers for now.